So our first part of transformations is going to center around just the XY coordinate. So we're going to look at a single point. And the reason why we're going to center our attention on a single XY coordinate is because once we conceptually understand how to move that around through a single transformation or maybe a composition of multiple transformations, we can carry over those ideas into an actual function graph, say f of x, and be able to move this whole series of points that forms that function. So again, the center of attention for this video will be focused or directed towards the single xy coordinate. But before we jump into each transformation type, we're going to take a look at what the xy coordinate reveals to us. What information is embedded in those two numbers? So what does the xy coordinate tell us? Well, the first viewpoint you can take is that it gives you a location. So location on the xy plane. When you're on a two-dimensional surface, like the xy plane, you only need two numbers to pinpoint your location. Now, real-life example is longitude, latitude. That will give you a location on the surface of the Earth, right? So any two-dimensional surface, 2 points gives you a location. So what about the breakdown of each piece? So we get two numbers. What does each number tell us? So the x-coordinate value is going to tell us horizontal distance and direction. From the y-axis. The y-coordinate will tell us vertical distance and direction from the x-axis. So that is our first perspective. But the second perspective, and an often forgotten one, is that it tells you the inputs and outputs for a function. In a later video, we'll dive deeper into what functions are and how they work, but an input and output at a specific location is valuable information given certain problems. Okay, so the input-output perspective, we can say the x-coordinate that tells you the input, or essentially what you're plugging in. Into the equation or function. The y-coordinate will represent the output. So what that's revealing to you is what comes out when plugging in x. So two perspectives. You can think of it as a location, or at a specific point, it gives you the input and output at that point. Okay. So now let's jump into the actual transformations. So the first one is a translation. A translation is a shift or a slide. And we have two types. We can move horizontally or vertically. So we'll break that down into those two categories. So let's look at the horizontal and then vertical. So there's two possibilities for each. Actually, let's distinguish these with different colors. So let's actually just take care of horizontal first. So if I have my coordinate plane and I place a point at, say, we'll call this 1, 2. Now, if I want to move over to the point 6, 2, that would shift that point to the right. Now, how far to the right are we going? That would be adding 5 units to x. So again, if I'm just shifting right, it looks like I'm not trying to go up or down. So my y coordinate at these 2 points will be the same. They're both value of 2. But if I want to move it to the point 6, 2, again, I can see that that would be a shift or a slide to the right. And again, from an operation perspective, what happened? We added 5 to the x coordinate. But let's say I wanted to shift this thing left 3. If I move it left 3, if I count 3 spaces to the left on my coordinate plane, that will place me, now this isn't actually drawn to scale very well, so let's shift that over a little more. So not drawn to scale, but actually let's say it's going the same distance. So that's going to bring us another 5 units left. What point would I be at? So again, if I just count off 5 units to the left, operationally what happened? In this case, we subtracted 5 from the x coordinate. So in a general sense, we want to generate an abstract rule. If we start with some xy coordinate, and we add some number k to just x, where k is a positive number, that will move the thing right. You will go right k. So let's actually put that in a different color. So this will go right, whatever that number k is. If we were to subtract some number from x, where that number we are subtracting is positive, again, these are important conditions, then we're going to go left k. So that takes care of horizontal movements. Now let's look at vertical. With vertical, if we have an xy coordinate, and we want to shift it up, if we go back over to our graph, if I want to move this thing up, say 5, well, what coordinate does that bring me to? Now I'm going to be at the point, again, I'm not moving left or right, so my x coordinate is not going to change, but rather my y coordinate will change this time. And I went from 2, and say I want to go an additional 5, that would bring me up to 7. So again, what happened here? We added 5 to y. And I bet you can make the conclusion now, if you wanted to go down 5, that would be subtracting 5 from the y coordinate. Now where would that put us? At 1, -3. Okay, so to make some abstract rules, if I want to shift or slide vertically, we're going to add and subtract values, positive values, from the y coordinate. So if I add some number k, again, where k is a positive number, that will do something. And if I subtract k, where k is a positive number, that will also move it. Now, how does it move? If we're adding a positive number, we are shifting in the positive direction, so that would go up, whatever value k is. If I subtract, we're moving in the negative direction, so that will go down, whatever our value k is. So that is how we translate, and you'll notice that the operation that is used for these, so we can make a note, the operation for a translation or associated with translation is addition, subtraction. And again, I want you to take note of these conditions. That's really important, okay? Because if we start changing the conditions, then we have to change the overall abstract rule that we wrote. So those are necessary. Now let's jump over into the next type of transformation, which is the reflection. The reflection is going to be a flip over some line, which is going to place the point in a mirrored position which means if it's in a mirrored position, it should be equidistant. So points, we'll actually star this. Points should be equidistant from line of reflection. So our before and after points should be equidistant from that line of reflection. Again, we're just going to look at two specific cases. It's going to be over the x-axis and over the y-axis. So if I want to do a horizontal reflection, that is going to be over the y-axis. And anytime we want to do a horizontal transformation to an xy coordinate, we are altering the x value of that coordinate. So if I look at a quick example in a coordinate plane, where say I'm at the point 2, 3, and we want to reflect this across the y-axis to a point that would be equidistant from that line of reflection as before. So it's currently 2 units away from the y-axis. So to get the proper mirrored position, it would also need to be 2 units away from the y-axis. So where does that put us? Again, I'm not shifting anywhere vertically, so the y coordinate or the y value stays the same. The difference, again, how far away from the y-axis am I? Well, we're moving in the negative direction, so it's negative 2, 3. Let's say with that same point, I wanted to reflect it over the x-axis vertically. So we can add in that. So vertical reflection would be over the x-axis. Again, we're thinking about the movement itself. So don't confuse the direction in which each axis runs with whether or not it's horizontal or vertical. Think of the movement over that particular axis. That indicates what type of transformation it is, whether it's horizontal or vertical. So over the x-axis is a vertical movement. In this coordinate, it was 3 units away from the x-axis. So to get that mirrored position, it must also be 3 units away. Again, no horizontal movement done. So the only thing that changes is that y-coordinate. And we go 3 in the negative direction. So there's our resulting point. Now let's create the abstract rule for each. If I have a general xy coordinate, to reflect it over the y-axis, to perform that horizontal reflection, we must, if you look at the before and after image, we have to look or multiply the x-coordinate by -1 and leave the y-coordinate unaltered. For vertical, if you look at the before and after coordinate, you can see that if we take any xy coordinate and multiply it by -1 for the y value, we'll get a reflection over the x-axis. And these are the only reflection types we are responsible for in this class. So operationally, what are we doing? With translations, we said it was addition, subtraction. For a reflection, the operation is very specific. It is multiplying by specifically -1. So anytime we see an application of multiplication by -1, we know we have a reflection. And then lastly, we're going to look at a dilation. And the dilation is going to be an expansion or a contraction away from a particular axis. So expansion or contraction from or to an axis. Some synonyms that you'll see for each of these terms. For expansion, you'll see stretch. I will use that often. In contraction, we'll use compression. So visually, what's going to occur with a dilation is that we're going to get some magnification by some scale factor. and we'll call that scale factor k. Okay, I'm going to use the number k again. Now, the value of k, depending on what range of values it falls in, will dictate whether or not we have an expansion or a contraction. So just like the other examples that we've gone through, other types of transformations, we're going to be looking at horizontal dilations and vertical dilations. We'll just explore horizontal because the same procedure will be applied to vertical. So let's take a point. Let's say we're at the point 4, 6. Actually, let's do 2, 3. Again. So we're at the point 2, 3. And we want to do a horizontal stretch or a horizontal expansion. What that visually means is I want to pull this point away from the y-axis by some scale factor. So in the event of an expansion, let's say I want this point to be 3 times as far from the y-axis as it currently is. So in this current position, it is 2 units away. If I want this to be 3 times the distance, well then I need to bring this point out to 6, 3. Now, because that would be 6 units away. So what operation must I perform to get from that 2 and magnify it or dilate it or expand it out to that 0.63? You have to multiply by 3. Now, in a general case, for a horizontal stretch, again, this is an expansion. If we have, actually, let's just write the xy coordinate. If we multiply the x coordinate by some value k, now again, this condition's important, where k is greater than 1, we will get a stretch by k. Now, back to our point. Let's say I was starting at 6, 3, and I want to compress this point so that it is now half of the distance away from the y-axis as it currently is. So again, this thing is 6 units away. Let's say I want to compress this point back so that it's only halfway to the point 3, 3. So how do I halve the distance? Well, we are going to multiply by 1/2 in that case. So in general, if I have a point xy and I multiply it by a number, k, but again, this condition's important, where k is between 0 and 1, we will then have a compression by that factor k. So you're going to notice that dilations is just multiplying by some constant, but the thing you need to pay attention to, again, probably the most important part, is these conditions that are placed on our abstract rules. Anytime we multiply by a number greater than 1, we get a stretch. If it's between 0 and 1, we get a compression. And again, at the conclusion of this video, I'll show you a nice visual to support these claims, but let's jump over to the vertical dilations before we do that. So the application is the same in terms of the multiplication part, except this time, instead of applying it to the x-coordinate, because we want to do something vertically, we're going to apply it to the y-coordinate. So it's going to be x, k times y, where k is greater than 1. And then for the compression, we're going to multiply the y-coordinate by some number k that falls between 0 and 1. So again, what do these reveal? The same thing as before. So we'll stretch by k, in this case in a vertical direction. So think we're going to pull that point away from the x-axis, and then a compression by k would indicate that that point is getting squished or pushed towards the x-axis. So those are the three transformation types that we are responsible for in this class: translation, reflection, and dilation. So now that we have abstract rules for each, let's take a visual or look at a nice visual on Desmos to support our claims. So now that we're over to Desmos, I'm going to add in a point. Let's just call it, actually, let's do a series of points so you can see them all move together. So if we add in a table, let's just go from -2, -1, 0, 1, 2, and then we'll place these at different locations. Okay, so we just have a random set of points, and you can see all 5 popped up. Now, if we take the coordinate and what we want to do to this thing is move all these points around. So I'm going to keep them in a group so you can see the structure that's preserved through some of the different types of transformations. And then this is, again, when you look at a bunch of points together, this stretch and compression is a nice visual. So let's say we want to move all these points to the right. We established that to move something to the right, we have to add some number, we'll do k, to our x coordinate, where k, again, so I'm going to make this thing slide, but we want k to be positive, so it's got to be greater than 0. Okay, and then that's all we need for that. And we want to play this thing. I'll slow the speed down. We'll have it go in one direction. Go back to k. We'll have this thing start at 0. So we'll have it range between 0 and 10. Eliminate this. So if we pull it back, again, I'm going to slow the speed down. Okay, so k is going to be a positive number, and it's going to head towards 10. You'll see that this thing starts sliding to the right exactly as we predicted. So the white points are the transformations being applied. Our pink points are the original set. And you can see that when we add some positive number, this thing starts to slide to the right. If we are to subtract k instead, we'll bring these white points back to the starting position. So if we're subtracting a positive number, we expect that thing to move left. And when we play this, we can see all the points sliding to the left. And you'll notice that the distances between the points are preserved through a translation. So that's an important idea. Distances between the points are preserved through just the application of a translation. Now that's moving left and right, but there's nothing stopping us from moving this up and down. So I'm going to zoom out a little bit. And if we want to move it up, we add k. Again, we've already classified k as a positive number. So we'll bring those white points back to the starting point. When we play this, you can see them all slide up and distances preserved. If we want to move it down, we're just going to subtract a positive number. Instead, we'll bring this back to the starting point, play it, and you can see these all slide down. So again, addition, subtraction. Horizontally, if I want to move, I'm affecting just the x value of the coordinate. If I want to move vertically, I'm affecting just the y value of the coordinate. So we have all those points. Let's bring it back to the start. If I want to reflect this over the y-axis, I should see a mirror image of all the starting points. Over the y-axis is a horizontal movement, so I'm going to multiply the x-coordinate by -1. And you can see that now we have mirror imaging from our starting position, again, which are represented by the pink. And you can see that the points, the white points after the transformation, are equidistant from the line of reflection. So they are the same distance from that line as their starting point. So that's the horizontal. If I want to reflect this vertically, I multiply the y-coordinate by -1, and you can see it flips over the y. Okay. Now, which one? Now they look the same. So how about we just take any point, maybe to better. Let's actually move these into a positive. So this is our new starting point. This will be a better visual for the vertical. So here's our starting points. Once I apply the vertical reflection, I multiply y by -1, you can see all these points flip over the x-axis. So we can see the mirror imaging, okay? So there's a better visual for the vertical reflection. Starting, multiply just the y, flips over the the x-axis. So there are reflections. And then lastly, let's perform some dilations. So we'll do horizontal dilation first. Let's do a horizontal expansion or a horizontal stretch. So if I want to stretch something, I need to multiply by something greater than 1. So I'm going to reset my condition on k to be greater than 1, and it'll stop at 10. So if I multiply the x, because again, I want to do a horizontal stretch, so I'm going to affect the x coordinate, I multiply them by k, and if I play through, we should see this thing being pulled away from the y axis, and you can get the visual for the dilation. So all these points are being stretched away from the y-axis. You can see distances are not preserved with dilations. Okay, so an interesting note, distances are not preserved between 2 points. So that is a horizontal stretch. Now we can look at a vertical stretch. So I'll zoom out to get a better visual. So if we multiply y by that number that's greater than 1, we should see a vertical stretch. So I'll bring this back to its starting point. Now as we play through this, we should see these points being stretched away from the x-axis. And that's exactly what we see again. Distances are not preserved between our points from their starting distances. They're actually growing in length, hence the stretch. So those values are being pulled away in that case. Now let's look at a compression to end the video. So if we want to do horizontal compression, we're going to change the k values to range just between 0 and 1. And when we play through this, you'll see that these points get pushed towards the y-axis. So you can see that occurring now. So when k is between 0 and 1, I'm going to get a compression by that factor. Okay? So again, horizontal, I'm just going to multiply the x. If I want to do a vertical compression, we're going to multiply the y by a number between 0 and 1. And when I play through this, you'll see that they get squished towards the x-axis. So you can see these things are being compressed down. So there are the visuals for all of the transformation types. Make sure you have your rules written down somewhere, and we will look at some actual problems or practice problems relating to those as we move forward. But that is a general overview for how to transform a single point or a group of points like in this.